Uh, Triple integrals is the next topic. As you can easily visualize, a triple integral will have three integral operators. So we will have a triple integral operator, then a function of generally three variables, f of x, y, z, dv. dv is called the volume element, which in Cartesian coordinates is written as dx, dy and dz. Now as the domain changes, suppose you are into a spherical coordinates domain or a cylindrical polar coordinates domain, then dv is appropriately replaced where the concept of Jacobian will enter. Right now let us discuss triple integrals in the Cartesian frame. So as I told you, triple integral f of x, y, z dv generally should be understood as finding out the mass, but for that f of x, y, z should be the density function. Now let us take the evaluation of triple integrals through a few simple examples before going again to application oriented problems and change of coordinates through transformations. The first problem that I have chosen is the integral from 0 to 1, 0 to x, 0 to x plus y dz dy dx. Now how do you decide the order of integration? Now when the inner limits are functions of x and y, then the first integral will be with respect to z. So once the integration with respect to dz is over, we are left with the x and y variables. Because the intermediate integral is carrying functions of x, it has to be with respect to y. And finally you will be left with integration with respect to x. So the technique is very simple. You have to follow very clearly what are the limit structures right from inner to outer. This is the innermost integral, this is the middle integral, this is the outer integral. So functions of x and y here means z first, functions of x here means y, then finally with respect to x. So we'll integrate this with respect to z first. Now here the student can use slightly faster methods. Instead of integrating three separate terms, you can understand that x plus y contains no z, therefore can be treated as constant. So you can integrate this as x plus y into z, because this is a constant, plus z square by 2 from 0 to x plus y dy dx. So when you apply the limits, you will get 0 to 1, 0 to x, x plus y whole squared plus x plus y whole square by 2 dy. These two can be combined and you can make it 0 to 1, 0 to x, 3 by 2 x plus y whole squared dy dx. Again, the student need not expand this and then integrate. X is a constant, therefore you can directly integrate this as x plus y whole cube by 3. So when you apply the limits, you will get 2x whole cube by 2 dx. So this is 8 by 3, x power 4 by 4. Of course, the lower limit of integration is also there. So there is a small modification here, minus x cube by 2. So we can make it 8x cube minus x cube as 7x cube by 2 dx. 7 by 2 x power 4 by 4 from 0 to 1. That leaves 7 by 8 as the output. So even a simple problem like this can sometimes make it extremely long if the student is not cautious. So he should not get into the trap of expansions. He must be very economical about the integration. So 7 by 8 is the correct option. and this happens to be option B. Question number 2. There is nothing about the limits, but it is the integration that many students may falter. So again, you can observe that the inner limits of integrations carry x's and y's. Therefore, the first integration must be with respect to the variable z. And then in the intermediate integral, you have got x here. Therefore, it has to be dy, not dx. So once dz and dy integrations are over, you are left with the x integration. So let's first integrate this function with respect to z. So 0 to pi by 2, x to pi by 2. The integration of the cosine function is sine function, sine z by x, divided by the coefficient of z, which is 1 by x. So we can write 0 to pi by 2, x to pi by 2, x sine z by x, 0 to xy dy dx. So the variable z will be substituted with xy and then 0. Of course, sine 0 is 0, therefore the lower limit does not have any effect on the function. So 0 to pi by 2, x to pi by 2, x sine xy by x leaves y dy dx. So now the problem is in control. The integration now is with respect to y. So let me show you the details of this integration. The integration of sine y is minus cos y. So we can put the minus outside. 0 pi by 2, x sin y becomes minus x cos y from x to pi by 2 dx. Integration of sin y is minus cos y. So when you apply the upper limit pi by 2, cos pi by 2 leaves 0. So you will have minus 0 to pi by 2, 0 minus x cos x dx. So this is integral 0 to pi by 2 x cos x dx. And if you integrate by parts, you will get x sin x plus cos x from 0 to pi by 2. So this will give us pi by 2, sin pi by 2 is 1 plus 0 minus of 0 plus 1. So pi by 2 minus 1 is what we get. So as you can see, the challenge is only here. After that, it's all very, very simple. But still this can be challenging some students. So the correct option for this problem is C. Let us go to the next question. Question has been chosen because sometimes the student may be confused about fixing the order of integration. Unlike the last two problems, where the innermost integral carried functions of x and y, here there is a small dilemma. The innermost integral carries y, so the student has to decide whether it is dx or dz first. When he cannot decide on the basis of this, he must take the combined information from these two integrals. He will find x and y are involved. Therefore, the dz integration will become the first integration. That is how the conflict is resolved. Now, once dz is cleared, he will find functions of x here. Therefore, dy is the next order and obviously dx becomes the third order. So there is not much in this in terms of integration, but it is only the fixation of the order of integration which matters. However, let me show you the solution. 0 to a, 0 to x, x y, z square by 2 from 0 to y, dy dx. So this will leave half integral 0 to a 0 to x xy cube dy dx. No challenge. Xy power 4 by 4 from 0 to x dx. Apply the limits and you'll have 1 by 8 0 to a x to the power of 5 dx. So 1 by 8 x power 6 by 6 from 0 to a. So it is easily a to the power of 6 by 48, and the correct option is A. So one has to practice a few questions to know how to fix the correct order of integration. Let's go to the next question. In this question, let us see how the order has to be fixed. Of course, there is no challenge in the integration part. Now, the innermost limits carry functions of y and z. So, when you fix the order, it will be dx first. Once integration with respect to x is cleared, now we are left with dy and dz. Because you got functions of z here, obviously it has to be dy followed by dz. So let's perform this integration. 0 to 1, 1 to z. Remember, with respect to x first, so x square by 2 yz from 1 to z dy dz. So 0 to 1, 1 to z. We can keep this half outside. Replace x with z. You will have yz squared minus x is 1 will give yz dy dz. So let's do the integration with respect to y. So this will be half 0 to 1 y square by 2 z squared minus y square by 2 z from 1 to z dz. So let's substitute. Replace y with z. You will get z power 4 by 2 minus z cube by 2 minus of z square by 2 minus z by 2. So let's integrate this. Z power 5 by 10 minus z power 4 by 8 minus z cube by 6 plus z square by 4. So half 1 by 10 minus 1 by 8 minus 1 by 6 plus 1 by 4 with lower limit contributing nothing. So if you can evaluate the LCM of these numbers. So let's look into the 8, 6 and 4. The LCM would be 24. So the LCM of 24 and 10 will be about 120. So half into 120 here, 12 minus 15 minus 20 plus some 30. So 42 minus 35 will be 7 by some 2. I hope you can check that once again. But this is the answer, and the correct option happens to be A. This problem has been selected because the limits of integration are not directly provided. The student has to study the equations given carefully and then fix the limits of integration. Now you can see that the four equations which are given here are all planes. X is equal to 0, y is equal to 0, z is equal to 0 corresponds to the coordinate planes, and there is an inclined plane x plus y plus z is equal to 1. We know from three-dimensional geometry, when four planes are involved, then a tetrahedron will be formed. So the solid of integration here is a tetrahedron. One can analyze the tetrahedron, draw it graphically and then fix the limits, or there is a very simple way by which one can write the limits. Suppose you decide to integrate with respect to z first, then you can take the lower limit of z from here and the upper limit of z from here. Once the integration with respect to z is over, the number of dimensions collapses from 3 dimensions to 2 dimensions. So we are on the plane. On the xy plane, y varies from 0, because that's given here, to y is equal to 1 minus x. Finally, x varies from 0 to 1. So these are the limits of integration for this integral. So if you fix the limits 0 to 1, 0 to 1 minus x, 0 to 1 minus x minus y, x, y, z, dz, dy, dx. So let's perform this integration. Integration with respect to z first, x, y, z square by 2 from 0 to 1 minus x minus y, dy, dx. So when you apply the limits for z and keep 1 by 2 outside, xy into 1 minus x minus y whole squared dy dx. So here one has to be careful. Again, there is a trap. 1 minus x minus y whole squared direct expansion will take you to 6 terms. That will make it 6 integrations at the next stage. But if you are a bit careful and know about which variable you are going to integrate, then we can minimize the expansion. Because the integration is with respect to y, this can be treated as a constant. So this is just an a minus b whole squared expansion. Half 0 to 1, 0 to 1 minus x, xy into 1 minus x whole squared minus 2y into 1 minus x plus y squared dy dx. So now it's only the question of integrating 3 terms with respect to y. So 0 to 1, x into 1 minus x whole squared will remain constant. Integration of y is y square by 2 minus x into 1 minus x remains constant. Integration of, there is also a 2 here. Integration of y square is y cube by 3 plus x into y power 4 by 4 from 0 to 1 minus x dx. So when you apply the limits of integration for y, you will get half integral 0 to 1 x into 1 minus x whole to the power of 4 by 2 minus 2x into 1 minus x whole to the power of 4 by 3 plus x into 1 minus x to the power of 4 by 4 dx. Fortunately for us, all the terms are similar with different denominators. So if you take the LCM of 2, 3 and 4, it is 12. So this will be 6 times this will be 4 times and that will be 3 times. So this will be 6 minus 8 plus 6 here. Let's make it clear. Half, 0 to 1. Let us say 12 is LCM. So this will be 6 x into 1 minus x to the power of 4. 3 goes 4 times, so we'll get minus 8x into 1 minus x to the power of 4, and then that becomes 3 times. So 3 times x into 1 minus x to the power of 4 dx. So if you reduce it, it becomes 6 plus 3 9, 9 minus 1 8. So let me show you the concluding part here. So this will be 1 by 24, 0 to 1, x into 1 minus x to the power of 4 dx. Now again, there are several ways of doing this. If you fall into the trap of expanding 1 minus x to the power of 4, you will get 5 terms. So we should avoid that situation. Now we already have a very sound knowledge of gamma and beta functions. I will convert this into a beta function now. So what I do is, I will write this as 1 by 24, 0 to 1, x to the power of 2 minus 1, 1 minus x to the power of 5 minus 1 dx. So this is 1 by 24 times beta 2 comma 5, which I will convert into gamma functions. Gamma 2 into gamma 5 by gamma 7. So this will be 1 by 24 into 1 into 4 factorial by 6 factorial. So this 4 factorial will cancel 6 factorial 30 times. So therefore we will get 1 by 720. And option A is a correct option for this one. So what did we understand from this example? Basically what we have understood is, if you are given the region bounded by some planes, then you must first see which is the easiest way to fix the limits of integration. Fortunately in this problem, all the equations represent planes, so it was easy to fix the limits of integration. Once that is done, there is hardly anything, but don't fall into the trap of expanding large algebraic expressions. You should economize on integration. And once that is done, the best part of this problem is the concluding part, where we have introduced the beta function to finally evaluate. Otherwise, 1 minus x to the power of 4 leads to unwanted complications, thereby delaying the answer. Let's go to the next question. It's a very interesting problem. Even though the problem is set to Cartesian coordinate system, but can one observe the integration can get complicated after the stage 1 integration is over because of the radicals and all that. So if you observe this situation, there are two important indicators. The first indicator is, in the function we have got 1 minus half x square plus y square plus z squared. And not only that, if you look at these limits which are standing for z, then there is a very good geometrical idea behind this problem. So if you take z is equal to 1 minus x squared minus y squared under root, and if you simplify this, you will get x squared plus y squared plus z squared is equal to 1, which is a sphere. Of course, radius is 1, so we can call it a unit sphere. That is observation number 1. Observation number 2, look at the lower limits of integration, they are all 0. So this sphere is located in the first octant. So we are integrating over 1/8 of the sphere. So if you keep this in mind, then this integration can be completely transformed in terms of spherical polar coordinates. So transform into spherical polar coordinates. I hope you are all aware x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta are the transformation equations from Cartesian to spherical polar coordinates. But you must know two important things here. Suppose you square and add, then you will get x squared plus y squared plus z squared is equal to r squared. And not only that, the Jacobian dou x y z by dou r theta phi will be r square sin theta. So these are two very important results connected with this transformation. So now if you introduce these transformations into this, and not only that, we note that r varies from 0 to 1, theta varies from 0 to pi, phi varies from 0 to pi for the complete sphere. Or the complete sphere. But let us not forget, we are integrating only over the first octant of the sphere. So there are couple of ways to handle this situation. What we can do is, we can just use a multiplication factor 1 by 8 because we are integrating over first octant, and use the full limits of integration 0 to 1, 0 to pi, 0 to 2 pi, dx dy dz becomes r square sin theta, because this is Jacobian, dr d theta d phi divided by the square root of 1 minus r square, because x square plus y square plus z square is r square. Now let us see. This was the original problem, that is a transformed problem. Which one is tougher? It all depends on the student. This can be easily cleared, but we will do one thing. We will change the order. I will take these as r limits. R is equal to 0 to 1. This is theta and this is phi from 0 to 2 pi. So we will first integrate with respect to r, then with respect to theta, then with respect to phi. So first we have to clear this integration. That integration has to be cleared first. So what I'll do is, I will take this integration just on the sideline. It's a very small operation. What I'm trying to show is 0 to 1 r square dr by square root of 1 minus r square. So if you can clear that integration, the next two stages are very easy. Now for this there are a couple of techniques, but the easiest technique is introduce a substitution r is equal to sin alpha. So dr will be cos alpha d alpha, and when you change the limits, you will get 0 to pi by 2, r square becomes sin square alpha, then square root of 1 minus r square will be square root of 1 minus sin square alpha, that is cos square alpha. Square root of that becomes cos alpha, and that cos alpha cancels with this cos alpha d alpha of the numerator. So you are left with just the integration of sin square alpha d alpha, and I hope you easily remember this result. Integration of sin square alpha from 0 to pi by 2 is always pi by 4. You can keep it as a very small result always to be used. So now with this integration over, we can substitute pi by 4 in this area. So what happens? We will get pi by 32. The next integration with respect to theta. So when you integrate sin theta from 0 to pi, you will get minus cos theta from 0 to pi. So that becomes nothing but 2 d phi. 2 because the integration of sin theta is minus cos theta from 0 to pi, you will get 2. So you will get pi by 16 into the integration of d phi is 5 into 2 pi. So we'll get pi square by 8. So this problem has got very good challenges, and it all depends upon recognizing you're integrating over spheres, therefore shifting to spherical polar coordinates, Jacobians, etc. And then one small integration challenge in the initial stages. This itself can be very difficult for some students, therefore I wanted to show you that. And the later stages are very easy to understand. So option D is the correct answer for this problem. Let's go to the next question. Now this is another problem that we have selected to understand integration over spheres. Much easier than the last problem, but now the integration is over the entire volume of the sphere. So therefore transforming into spherical polar coordinates r varies from 0 to the radius of the sphere, theta varies from 0 to pi, and phi varies from 0 to 2 pi. So if you, of course, Jacobian is r square sine theta. So dv is equal to mod j dr d theta d phi. So the integral will be 0 to 2 pi, 0 to pi, 0 to b, r square whole inverse into r square sine theta dr d theta d phi. So the first integration with respect to r, so you will have 0 to 2 pi, 0 to pi, r from 0 to b, sine theta d theta d phi. So this will give us b, and the integration of sine theta from 0 to pi will be 2. Therefore you will have 0 to 2 pi 2b d phi. So this is 2b into phi from 0 to 2 pi. So we'll have 4 pi b, and the correct option is B. So the reason why we have selected this question is once again to observe the presence of x square plus y square plus z square in the function, and the integration is taking place over a sphere. This is an ideal condition by which we can quickly solve the problem. If the same problem were to be solved in Cartesian, that would be very cumbersome. So this is how transformation should be exploited in order to evaluate triple integrals quickly. Let's go to the next question. In this question, we have to triple integrate x square plus y squared, and the solid is a little bit typical. It is bounded by the plane z is equal to 0, which is xy plane, and there is a paraboloid z is equal to 9 minus x square minus y squared. Now obviously this is not a case where we can use spherical polar coordinates, but if you can use cylindrical polar coordinates, the problem can be solved very quickly. Now what are the transformation equations for the triple integrals in cylindrical polar coordinates? So I will write transform into cylindrical polar coordinates. X is equal to r cos theta, y is equal to r sin theta, z is equal to z. The Jacobian of this transformation is r. So dv is equal to mod j dr d theta dz. So therefore, and you can observe x square plus y squared will be r square. So this x square plus y square in the function will be replaced with r square, and dv can be replaced with that. Jacobian is r. So therefore, I is equal to triple integral over v r square into r dr d theta dz. Well, we need limits of integration. You can easily see z varies from 0 to 9 minus r square, and once you put z is equal to 0 into this equation, you will get x square plus y square is equal to 9. Therefore, r varies from 0 to 3 and theta varies from 0 to 2 pi. So therefore, you will have 0 to 3, 0 to 2 pi, 0 to 9 minus r square, r cube. First we'll do with respect to z, then theta, then r. So this will be 0 to 3, 0 to 2 pi. So r cube z from 0 to 9 minus r square d theta dr. So this would become 0 to 3, 0 to 2 pi, 9r cube minus r to the power of 5 d theta dr. Of course, d theta dr or dr d theta is the same, but because we have fixed the order like this, let's finish with respect to theta. So now you will have 0 to 3, integration of d theta is theta, so you will get 2 pi into 9r cube minus r power 5 dr. So this will be 2 pi into 9r power 4 by 4 minus r power 6 by 6 from 0 to 3. So this will be nothing but 2 pi, this will be 3 power 4 into 3 square. So that will be 3 power 6 by 4 minus 3 power 6 by 6. So this will be 2 pi 12. 4 goes 3 times, 6 goes 2 times. So 3 minus 2 is 1. So we'll get 3 power 6. So we can call this pi by 6. 6 we can write as 2 into 3 into 3 power 6. So 1 3 will get cancelled. So we'll have pi into 3 power 5 by 2. So this will be 243 pi by 2. And the correct option for this problem is A. So what is that we have learned in this question? The observation is when z is equal to 0 is substituted here, you will get x square plus y square is equal to 9, which is actually a cylinder in 3 dimensions. Therefore, cylindrical polar coordinates is the idea behind this problem. But you must remember all the transformation equations. Cylindrical polar coordinates transformations are these. You must know the Jacobian, and then you must know how to fix the limits of integration. The crucial part is the fixing of z limits. How did we get z is equal to 0 to 9 minus r square? Well, z is equal to 0 is already specified in the problem. and because x square plus y square becomes r square, therefore you get 9 minus r square. So once you have z is equal to 0 to 9 minus r square, you are now into the two-dimensional plane. So you must visualize what is there on the two-dimensional plane. That is very easy to understand once you put z is equal to 0. When you put z is equal to 0, you will get x square plus y square is equal to 9, which is a circle. So that is how we have fixed the limits of integration in polar for the circle as r is equal to 0 to 3 and 0 to 2 pi. The integration part is very simple to understand. Let's go to the next question. Let's find out the mass of this solid. It's a tetrahedron bonded by coordinate planes and a plane x by a plus y by b plus z by c is equal to 1. So mass is equal to volume integral f of xyz dv. So in this question, we'll have 0 to a, 0 to 1 minus x by a, 0 to 1 minus x by a minus y by b, kxyz dz dy dx. Here z limits will be 0 to c into 1 minus x by a minus y by b. Y limits will be 0 to b into 1 minus x by a, and finally x is equal to 0 to a. So I will show you the initialization kxy z squared from 0 to c into 1 minus x by a minus y by b dy dx. So k can come out, 2 can come out, and when you substitute z is equal to that, you will get a c squared. So therefore k c square by 2, 0 to a, 0 to b into 1 minus x by a xy into 1 minus x by a minus y by b whole squared dy dx. So let's expand this with this as constant, and you will have k c square by 2, 0 to a, 0 to b into 1 minus x by a, xy is there, 1 minus x by a whole squared minus 2y into 1 minus x by a plus y squared by b squared dy dx. So this integration with respect to y should be carefully handled. So you will find x into 1 minus x by a whole squared coming everywhere. So just k c square by 2, 0 to a, you will have x into 1 minus x by a whole squared into y square by 2 minus 2x into 1 minus x by a into y cube by 3 plus x by b squared into y power 4 by 4 from 0 to b into 1 minus x by a dx. So when you substitute y is equal to b into 1 minus x by a everywhere, so you will get a b square term here, and then here also you should observe, but everywhere 1 minus x by a will be dominating. So I will leave this integration. Please refer to an old example, because you have to manage your they are all one and the same types of terms. Here the denominator is 2, here the denominator is 3, here the denominator is 4. So you have to just take LCM, combine all the terms into a single term, and then just manage the integration. k a square b square c square by 720 is what is expected that we should be getting. So correct option for this problem is C. Kindly verify that. I advise again students to involve the beta gamma functions in the last stages by introducing a small substitution x by a is equal to t. Let's go to the next question. This is a volume application, and all of us know when the density function is equal to 1, we get volume. So volume is equal to triple integral 1 dV. This one is density. So first what we do is we fix the limits of integration for z. 12 plus y minus x squared dz dx dy. So double integral over r. Integration of dz is z. So 12 plus y minus x squared dx dy. Now this r is the region in the xy plane. So let us try to draw this region. This is y is equal to x squared, and this is x is equal to y squared. So this is the region of integration with intersection point 0, 0 and 1, 1. We will call the region Rx. X varies from 0 to 1. This is the lower limit of y. This is the upper limit of y. Y is equal to x squared to y is equal to square root of x. So we have to integrate this double integral with these limits. So volume is equal to integral 0 to 1 x square to square root of x 12 plus y minus x squared dy dx. So 0 to 1 12y plus y square by 2 minus x square y from x square to x dx. So I'll just substitute the limits for you. 0 to 1 12x plus x square by 2 minus x cube minus of 12x squared plus x power 4 by 2 minus x power 4. So you have to just combine the terms. There is only one x term, but there are two x square terms, one x cube term and one x power, two x power 4 terms which can be combined to make it into a single term. And this integration I think students can very well manage, and you can check the correct option will be A for this problem. You can easily do because there is hardly any challenge in this question. Next problem. This is a volume application where in the double integration stage we can introduce plane polar coordinates. Again, the density function will be 1 for all volume applications. So volume is equal to triple integral 1 dV. First we integrate with respect to z. Z is equal to 0 to 0 because the solid is bounded by xy plane, and the equation of xy plane is z is equal to 0 to 12 minus 2x minus 3y divided by 4. So we'll have double integral over r 12 minus 2x minus 3y by 4 dx dy. In fact, I have not shown the first integration. Once you write dv as dz dx dy, the first integration with respect to z will give us this because of the limits. So take 1 by 4 outside. 12 minus 2x minus 3y dx dy, and this region R will be x square plus y square is equal to 1, which is a circle. So use x is equal to r cos theta, y is equal to r sin theta, Jacobian is r varies from 0 to 1, theta varies from 0 to 2 pi. Once it is done, it's very straightforward. 1 by 4, 0 to 2 pi, 0 to 1, 12 minus 2 r cos theta minus 3 r sin theta r dr dt. Now for students with good practice of integration, they'll realize that this term and this term, both of them vanish. Because when you integrate cos theta or sin theta between 0 to 2 pi, you get zeros. That means only this term is left. So we have to integrate 12r. So you will get 1/4 0 to 2 pi 12 r square by 2 from 0 to 1 d theta. So the value of this is 6. 6 by 4 0 to 2 pi d theta. So 6 by 4 into 2 pi. So you'll get 3 pi. So 3 pi is the correct option for this problem, and this option is C. So what we have learned in this example is how you don't have to continuously integrate over the Cartesian coordinate system. You can partially do with respect to z, first clear with respect to z, and the remaining double integral you can convert using plane polar coordinates. So these types of mix is very important in these types of problems. Let's go to the last question. We want to evaluate the volume of an ellipsoid. Volume of an ellipsoid x by a whole squared plus y by b whole squared plus z by c whole squared is equal to 1. Now there are two approaches. Obviously for an examination the competitive nature, we cannot do it by the longish procedures. So we'll introduce the concept of transformation, Jacobian, and thereby simplified triple integration. So what we do is we'll introduce x by a is equal to capital X, y by b is equal to capital Y, z by c is equal to capital Z. That is x is equal to a capital X, y is equal to b capital Y, z is equal to c capital Z. Let us find the Jacobian. Dou xyz by dou capital X capital Y capital Z. So this will be nothing but a 0 0 0 b 0 0 0 c, which is ABC. So therefore let us write the volume formula. Triple integral 1 dv over ellipsoid. This is the actual formula for the original ellipsoid. Now because we have introduced transformations, this equation becomes capital X squared plus capital Y squared plus capital Z squared is equal to 1, which is a sphere. So in a new reference frame, the ellipsoid can be visualized as a sphere. So what happens to this is triple integral mod j, let us say dv dash over sphere. So this is nothing but ABC triple integral dv dash over sphere. And we know this is nothing but volume of sphere. Without going into integrations, we can write 4/3 pi into r cube. The radius of the sphere is 1 because this equation represents a unit sphere. So you can say 4 pi ABC by 3 is the volume of the ellipsoid. Please observe that 4/3 pi a cube would have become the volume of a sphere. So it looks very consistent because when you make A is equal to B is equal to C, then that would become the volume of a sphere. So a sphere is a special case of an ellipsoid. So please observe the effectiveness of using the Jacobian as a very important tool in finding out fast triple integrals or fast double integrals. So with this we come to the end of the series of lectures on double and triple integrals. Thank you. The correct option for this problem is C.